If I briefly recap what we learned last time, we finished our discussion about like 1D photonic crystal, and then we proceed to the 2D photonic crystals, right? And in 2D photonic crystals, everything's are basically the same. The only difference is that if your photonic crystal becomes 2D, your Brillouin zone also becomes 2D. So you need to take into account, the K vectors in both direction, Kx and Ky. And also you need to think about the polarization of the light, right? And then we argued that if you have a cylindrical, periodically placed cylinders, you have TM band gap, but TE mode doesn't have a band gap. And the situation is the other way around if you have a fishnet type of a structure. So in order to open a band gap for both TE and TM mode, we need this type of like kind of hybrid sort of structure. And then we talked about these defects like point defect, line defect, and surface defect. So the main usage of these defects is that defects can hold localized mode, right? That's the most important thing. So that you can use it for multiple different purposes. And also 3D photonic crystals, like it's just more complicated, but basically the idea is the same. You have now 3D Brillouin zone, so 3-directional K vector. So it's just become a little bit more complicated, but the physics is exactly the same. Okay. Now, as a last topic, I also introduced about the different directions of phase and group velocity in photonic crystals. So like if you have a photonic crystals lying in 45 degrees like here, and then you shine light, which is denoted as a black arrow, and you have a reflected light, which is kind of very normal. But the refracted light, even though the refracted light has K vector along this direction, so it's like this direction, its group velocity is along this direction. And so if a material has no loss, the direction of a group velocity and direction of energy flow are same. So what you can imagine is that because the phase velocity is along this direction, if you draw an electromagnetic field profile, it's gonna look like this. Electromagnetic wave front is going to be perpendicular to the propagation direction. But its energy flow is actually going in this way, even though its electromagnetic wave front looks like this. So it's a bit confusing. So if you, let's imagine you have a wave packet, for instance. So let's say you have a interface here, and then you shoot a wave packet. So wave packet is just a localized like wave. And then in the free space, of course, if the wave packet propagates in this direction, your electromagnetic field wavefront is perpendicular to the propagation direction. And then reflected light, it's the same. It's like this. But the transmitted light is gonna look like this. So the wave packet is going along the group velocity, but its electromagnetic wave front is perpendicular to the K vector. So it should look like this. Okay, so that is one interesting aspect and which looks pretty non-intuitive, counterintuitive. Right. So today, I'd like to talk about a few applications of photonic crystals. I just want to be very brief, but just to cover like what kind of interesting devices can be created based on photonic crystals. So let's begin with waveguide. So if you have, like, we already learned about this waveguide thing, right? Like, sorry. Oh, what's wrong with it? Okay, yeah. So if you have a dielectric slab waveguide with thickness with a given thickness, you can see that the wave can can be guided along the waveguide, which is called dielectric waveguide. We know that how to solve dispersion relation of this dielectric waveguide. And you remember that the guided mode of this dielectric waveguide has this type of a dispersion relation, and then when these waveguide mode meets the light line, mode cutoff occurs. And this condition, if I recall you, coincide with total internal reflection condition, right? So if you, as the dispersion relation of the mode meets the light line, total internal reflection condition no longer holds, so that wave just leaks out to the free space, right? That's what we learned already. And then if we have a periodically placed dielectric bars, then as I said, because we have periodicity, our band structure or dispersion relation is repeated for every 2 pi, right? In K space. So that is effectively like this. You have, say, if I draw this thing, it's like you have a K vector, and then this is omega, this is light line, and then your dispersion relation must look like this, right? That's the situation here. And then if you have a periodicity, then what happens is that this type of a dispersion relation is repeated every 2 pi. So what happens is that effectively at the Brillouin zone, at the end of the Brillouin zone, so this is basically the end of the Brillouin zone. And then, so let's say this is the end of Brillouin zone. And then if you go 2 pi, then you have another light line coming in. And then another mode appears like this, right? Because everything is repeated. And then that forms this type of band structure, right? So this is kind of a band structure of this 1D photonic crystal. And as you can see, here, from here to here, we now have a band gap. There's no guided mode allowed in the waveguide. And here, the situation is very different, because if you look at here, no matter what frequency you choose, you're supposed to have a corresponding guided mode, right? And then if your frequency becomes above the cutoff of the second band, then you're supposed to have 2 guided modes. But here, once you have a periodicity, you have a kind of a localized band in K space, and you start to have a band gap. And in this band gap, no transmission or no guided wave is allowed. So where to use it? Well, you can use it to that's one example. And another example is that you have a 2D photonic crystal, which has band structure like this, okay? So here, the purple regime is where there is a photonic states. And in between, we have a band gap. So these region does not allow a wave penetration into it, right? There's no propagating mode in this 2D photonic crystals. But as I said, if you have a defect, right? So you see here, there is a smaller cylinders here. Then now it can support guided mode, okay? Because as I said, like in the band gap region, you have a imaginary K vector. There, even though there's no propagating mode, but there is a mode with imaginary K vector, so which looks like this in terms of a field profile. And then at the position of the defect, there's no problem that it supports a guided mode. So here I draw the dispersion relation of the guided mode as a function of the radius of this defect. Okay, so this defect radius is 0.1a, 0.12a, 0.18a, and then here this is 0.2a. The original thing is 0.2a. So once r becomes 0.2a, then it coincides with this band, the lowest band. But as it deviates from the regular size, you see here the guided mode can be supported. Okay. So this is waveguide application, and you can, because this bulk region, the bulk photonic crystal region, doesn't allow any wave propagation inside. This waveguide created by a line defect works surprisingly well. So if you create a waveguide band, like 90-degree waveguide band, it kind of route this guided mode without almost zero, with almost zero loss. And this is actually difficult if you think about regular dielectric waveguide. Okay, so imagine in dielectric waveguide, as I said, we can understand this as a propagation of rays, right? And then rays undergo total internal reflection and so on, right? But if imagine you have a 90-degree band, waveguide band, then what happens is that the angle of incidence basically changes as this ray meets the waveguide band. And then now this wave can leaks out to the free space, right? Because the total internal reflection condition can be broken at the band. So in order to create lossless wave routing, you always need to have certain a curvature so that this bending mechanism or guiding mechanism is not too much disturbed, right? So that's necessary to have a low loss waveguide bending. And then here, in this case, the situation is a little different because this waveguide does not rely on the total internal reflection. It relies on the fact that this photonic crystal has a band gap, so there's no allowed propagating mode. So no matter how steep your waveguide band is, there's no leak out, right? So that you can create a more efficient waveguide band, or waveguide like split. You have like Y splitter or even more ways to split your waveguide. And then you can also create, if you have a point defect, now you can create optical cavity. Okay, and I already mentioned about this multiple times, so I just don't want to go into too much detail. But what happens is that let's say this photonic crystal has some band gap. So here you have a band gap. Okay, and then at this band gap energy, if you have a point defect, because this photonic crystal region doesn't allow you to have a guided wave or propagating wave, it only allows you to have an exponentially decaying mode. And if you have a point defect, it can support a localized mode, confined mode, or cavity mode in a sense. And depending on how well this cavity mode couples to the free space, you can create a very high Q factor resonance. So Q factor here means you can just consider Q factor as a kind of lifetime of a cavity mode before it dies off. So let's say you excite this cavity mode, okay? And the amplitude of this cavity mode, of course, dies out as time goes by, right? So, after each oscillation, it loses its energy either by material loss or by exciting free space waves. It loses its energy, right? So that you have exponential behavior. And then quality factor tells you that how many times this cavity mode can oscillate before it dies out. And what I mean by die out is that its amplitude becomes 1/E of the original amplitude. Okay, so Q factor, you can interpret in this way. So Q factor of 1,000 means that this cavity mode can oscillate 1,000 times before it dies out. And then 100 is like it can oscillate 100 times before it dies out. Okay, so Q factor of 1,000 or like few thousand or even few tens of thousands can be created using a photonic crystal. And then how to use it? Well, here, this is one of the very famous work done actually at KAIST. So this work was published in Science in 2004, like long time ago, by Yong-hee Lee's group in physics department. And then the first author, Hong-kyu Park, is now a professor of Korea University. And this work was pretty famous because at this time, like 2004, there was not many papers appears in science, especially from Korea. So this paper got very popular right after it came out. So what they did was they created photonic crystal with a defect. So here you can see you have a photonic crystal, and then it's not just a point defect, but you can see your holes. The radius of the hole changes its size, right? Gradually, and then you have a point defect. So you can imagine like this entire thing act as a cavity, and then cavity mode looks like this, and the quality factor was about 3,000, and they was able to create a laser out of this cavity. Okay, so that was a pretty famous work at that time. And another application is you can use a filter out of photonic crystal. Like this is just a 1D photonic crystal, which is also called Bragg reflector, like alternating dielectric films. And then if you have a Bragg mirror, you can see here you have a band gap, right? And when you have a band gap, if you think about the reflectance, of course, there's no allowed transmission in the Bragg mirror. So like in the band gap region, so from here to here is actually here to here, reflectance becomes 100%, right? Without any almost zero loss, which is pretty interesting to me. So, and then of course you can shift the position of the reflection band or the width of the reflection band by changing the permittivity of the material or the thickness of the materials, right? So that's another usage of photonic crystal. So basically, it allows us to, how can I say, to control the transmission of a wave into the waveguide, and then just playing around this band gap and the defect, we can do many interesting applications. So another application you can also think of is this. Like if you, it's basically the same thing. You have a photonic crystal with a band gap at certain frequency omega, and then you have like a you know, it's not simple waveguide, but you have crossing bars, 2 crossing bars here. And then if you calculate the transmission of these crossing bars, what this guy do is that this bar partially reflects and then partially transmit some of the waves. So when these two, the interference between these 2 bars are constructive, then almost all the light is transmitted. Otherwise, it's going to be reflected. So you can see here, you have a very, very narrow transmission band in this waveguide. So if your frequency is like right at the transmission band, then you have almost 100% transmission. And then if your frequency is slightly different from that, you have almost no transmission. And you can see here, this is a log scale, right? So even with a small deviation from the transmission point, you get almost 0 transmittance. So this is just a kind of notch filter. Like it only allows you to have transmission at a very narrow frequency range. And of course, you can think of like all different combinations. Like here, you can also think of at certain frequency, the input light, the input wave guided mode is switched to the second channel, and in the other frequencies it goes to this way, and probably some other frequencies it goes to that way. You can engineer whatever way you want. So this is another basically application of the photonic crystals. And finally, I'd like to introduce you about photonic crystal fiber. And I'll just tell you 3 types of photonic crystal fibers. One is called a Bragg fiber. So here you have like alternating layers of materials placed in 1D basically, and of course your guided mode penetrate into the screen. And then second type is wholly fiber with a hollow core. So you have a hollow core, and then you have a photonic crystal here, and then here also like a photonic crystal, but there's no holes in it. So let me explain these 3 types of photonic crystal fiber like one by one. So the first one Now you can imagine how it is gonna flow, right? Because like, guiding mechanism is basically the same. If you have a photonic crystal, then what you want to do is you want to want this photonic crystal to have a band gap, right? And if you have a band gap, then at this frequency, this photonic crystal acts as a mirror. No light can penetrate into it, right? So that you can have a wave propagating along the core, right? So here you have two types of optical fiber compared, or guided waveguide compared. The first one is using photonic crystal, like 1D photonic crystal, so Bragg fiber. And in this case, as I said, so here and here you have propagating bands, like there is a photonic mode, and in the white region there's no mode, and you can see there are a bunch of guided mode allowed along the hollow core. Okay, but in this case, if you have a metallic waveguide, of course, metal is repelling electromagnetic wave at every frequencies. Right? There's no matter what frequency you shoot in, metal is gonna reflect anyway, as long as the frequency is much lower than the plasma frequency. So you have like bunch of modes exist regardless of the band gap of this thing. So, and then of course, like as I said earlier, you can classify your modes using first the polarization. So it's like TE polarization, and index, mode index 0, 1. In this case, 0 is angular index. So angular index of 0 means there's no node, no up and down along angular direction. And then radial index is 1, which means there's only one node in radial direction. Okay. And similarly, you can think of many other combinations, like if radial index is larger than 1, that means your mode is gonna look like this, like up and down in radial direction. And then if your angular index is higher than 0, that means your mode is going to be like plus minus sort of thing. So as you go to the angular direction, you have like multiple nodes exist, right? So these numbers are index, angular index, radial index, and then what's written here tells you about the polarization. And that was the same, we follow the same convention for instance, like a rectangular waveguide. In rectangular waveguide, we define it like TE and TM mode. And also if these mode, like let's say it looks like this, plus and minus, then this was like a TE 0, 1, right? Because it doesn't have any node at X direction, and it has only one node in Y direction. So similarly, if you have a circular symmetry, you define this in an angular and radial index. Right. And then if you think about the loss of this Bragg fiber as a function of core radius divided by A is the period of this photonic crystal, then as the radius becomes larger and larger compared to the period of the photonic crystal, your loss drops significantly. And then this ratio is 1 over R, it's proportional to 1 over R cubed. And if you think about like why this is happening, you can like understand this in this way. Like here, as R increases, then the surface area to volume ratio. So for instance, like most of the loss occurs. So if your waveguide, if your guided mode resides inside the core region, there's no loss because it's hollow core, it's free space. There's no loss mechanism. But the electromagnetic field resides in the Bragg reflector, even though there is a small, even though it's small, but there is a material loss. Okay, so as R increases, the ratio between this area to the surface decreases by 1 over R, right? Because area is proportional to R squared, but its circumference is proportional to R. So surface to volume ratio or circumference to area ratio is 1 over R. And the second thing is that not only that, as the radius of the core increases, if you compare the electromagnetic field amplitude at the center and the boundaries, it's proportional to the center area. So the field amplitude in the core is actually much stronger than the field amplitude in the cladding, and that's proportional also to 1 over R. Okay, so the field and this is field amplitude, so field intensity becomes 1 over R squared. So 1 over R from here, surface area to volume ratio, and 1 over R squared from field amplitude scaling gives you 1 over R cubed relation. Okay. And then if we move to a hollow core holy fiber, so let's say photonic crystal looks like this. And then this is a band structure again. And here we have a band gap as always. And then at this band gap, we can have a guided mode. Okay. So if we zoom this part up, it's like this. So if you zoom up this small rectangle, it's like this. And then in the band gap region, we have like a bunch of guided mode. And one interesting thing is that you have a guided mode with a wave vector smaller than the free space light, but also the wave vector larger than the free space light. So and then you can see their electromagnetic energy profile is very different. So if your wave guided mode has a shorter wave vector compared to the free space light, you can see here the electromagnetic wave is maximum at the center, right? It's kind of concentrated at a center. Whereas if the K vector is larger than the free space light, it's more concentrated on the surface. Okay. Why this is the case? Well, you probably remember this kx squared, ky squared, kz squared is epsilon omega c squared, right? This is the equation that all wave should satisfy, right? Because this is directly from the wave equation. And now we set kg as our propagation direction. And then this as just as a k perpendicular, for instance. And then let's say this is beta, okay? Now then k perpendicular squared is epsilon omega c squared minus beta squared. And then this is and if this is a free space, then this becomes k0 squared. like free space K vector, minus beta squared. So now things become more obvious because if beta, our propagating wave vector, is smaller than the free space K vector, like in these two cases, this value becomes positive, right? Which means your K perpendicular becomes real number, right? So if you draw a cross section, it's supposed to be oscillating, right? It can support like oscillating K vector at the core at least, right? And that's how you can have a field maximum at the center of the waveguide. On the other hand, if beta is larger than K0, this entire thing becomes negative, and then K perpendicular becomes imaginary, right? So then what happens is that in the core region, your electromagnetic wave, the cross-sectional view, must decay exponentially, right? So what happens is that like this is, you know, how can I draw it? It decays exponentially with respect to the surface, right? So that the field's supposed to have maximum along the surface because it's gonna decay as you move away from the surface, right? So if you have a high K vector, you're supposed to have a surface concentrated wave. If you have a low K vector, your wave can have a maximum inside the waveguide. Okay. Yeah, and like if you increase the air hole size, you can do many different things. Like in this case, there's no surface mode. You only have a kind of photonic mode. The field concentration is high in the core region. Right. And finally, what I'd like to show you is the solid core holy fiber. And in this case, it's not we are not using, how can I say, band gap of this fiber, but we just use like bunch of holes in order to change their effective index. So it's like this. You drill a bunch of holes, and the hole in permittivity is just 1. And then in the solid region, you have like index, let's say 2, right? And if your holes are spacing very nearby, so that the area covered by this material is much lower than the area covered by hole, you can say that the effective index in this region is in between 1 to 2, but it's closer to 1, right? And then if you think about this region where there's not much hole, then effective index is close to 2, right? So it's basically creating a dielectric waveguide with, for instance, like high index core, n equals 2, and low index cladding, n equals 1.2, something like that. Okay, and you use these holes to regulate the effective index of the material. And if you do so, of course, you can have a guided mode in the solid core. And what you see here is that if you draw the effective index of the mode as a function of lambda over a, so lambda over a means that the wavelengths compared to the basically the whole size. And then when lambda is much larger than A, like in this regime, you can see the effective index of the mode is relatively small, right? Because if lambda is large, then your mode is gonna spread out. Because lambda is large, your mode is gonna spread out to the throughout the entire fiber region. So it feels more holy regime, so that effective index becomes smaller. And if lambda is smaller than, much smaller than A, then you can support a mode with whose intensity, electric field intensity, is highly concentrated at the core, so that your effective index can be large. And also you can have like multiple modes. So you can support like higher order modes, like the lowest one and the second order, third order, and so on, right? So this is basically the scheme of photonic crystals. So if I recap like what we learned throughout this lecture notes, photonic crystals is just a periodically placed permittivity variation, right? So if you have a periodic variation of permittivity, then your electromagnetic wave must satisfy Bloch's theorem. And then because of that, band structure, what is called band structure, arises, like photonic band structure, like this, right? And as you change the permittivity of the materials and the lattice structure, lattice spacing, you can tune this band gap or the dispersion relation of the modes as you want, right? And then now you have a building block to use your photonic crystals for various applications. And here the applications are mostly based on the band gap, right? Like you could imagine that most of the photonic crystal applications are based on band gap and defect mode. So combination of the band gap and defect mode allows you to have a waveguide or optical cavity, filters, and so on, right? And finally, photonic crystal fibers. So I hope this was a comprehensive introduction about the photonic crystals. And I'll take questions. Okay, Jung Myung-gun asks, do we need to use photonic crystal even at the far distance from the waveguide? For example, at page 33, left photonic crystal. Oh, I see. So I guess what you are asking is that what happens if we remove this part, for instance, right? So that's your question. Yes. So, yeah, that is a very good point. And, nothing much is going to happen if we actually remove this, because what we need, so, you see here in the photonic crystal regime, in the band gap omega, you can see the field is decaying as you move away from the interface, right? So as long as you keep your photonic crystal thicker than the decay length, there's no problem. Yeah, that was a very good question. And is there any other question?
Okay. Berkay, I guess. Do you think photonic crystals are as important as they were before these days, or any new and exciting research still being done with them? This is also a very interesting point. Yeah, so in my opinion, maybe I'm wrong, but in my opinion, photonic crystals are pretty much understood now. So there's not many interesting physics left in terms of photonic crystal itself. And then in terms of applications, people now are casually using photonic crystal for like a waveguide filter or creating cavities. So in terms of new science, there's nothing much. And these days, people are more interested about topological aspect of photonic bands, and also like more advanced topics. So you can think of, like, in order to understand how this field is gonna move, you must see how condensed matter physics go. So if you think about the condensed matter physics, people, originally, like back in early 90s, they tried to understand how this electronic band gap appears, and then all these electronic phenomena and the lattice structure, how do they relate it? That was their topic. And now they're more interested in new kinds of materials having new, like, topological states, what is called, so that in photonics too, like people adopt those ideas, appeared in the condensed matter physics, and then translated into a photonic structure. So these days, many people are more interested in topological aspects. Yeah, and this photonic crystal itself is just, how can I say? It's a basic knowledge. It's not a new topic anymore. That was a nice question. And then Lee So-young at page 33, isn't there more reflected light than transmission? Oh, yes, this is also a very good question. Yes. So what Lee So-young said was like this. So what I said was, because we have a band gap here, there's no leakage allowed, right? So, but what I missed was that the possibility of this wave, incident wave, is just reflected back instead of get transmitted, right? And the fact that this photonic crystal has a band gap doesn't prevent the wave to get reflected, right? So in order to actually create a waveguide band, what you need to do is to actually minimize this reflection. So it's not as easy as I originally said. And then and in this example, it's been considered. It's, the reason why it's not having, say, for instance, like exact 90-degree angle is to prevent reflection, right? So at least in this example, there's no reflection, almost no reflection. And then here too, what you need to do is you need to play around with these two dots in order to minimize the reflection and maximize the transmission. Yeah, so it's not as simple as I originally said, but in these examples, there's no reflection.